Hello and welcome back to the show. My name's Relevant. This is Do All of the Things. On today's episode, Trainbox makes a return. That is my switch mode, power supply, variable output, motor controller, etc., that I use to run my model trains. And today it's getting upgraded for more power. Stay tuned. So in a previous episode, I acquired this TTC PCC streetcar train, an H.O. Bachmann, if you will. And I decided, you know what? I gotta pick up a little bit of track, see if I can get it running. And of course, me being me, it was an excuse to build a circuit. So I built this power supply controller for it. And I built it to run this thing. I had no idea that in a few months, I'd be stacking goats trying to pull 100-car consists. Basically, it's just one big snake game to me. Let's see how long I can make this train. But in order to do that, I need more power, more actual physical current. Now, initially I was running like a 900 milliamps, 20 volt power supply for this guy. And that did it for the smaller trains, but the longer they got, the more problematic it was. 900 milliamps, nowhere near enough. And this guy, well, I designed it around that 900 milliamps. I designed it with a capacity of about 1 amp with D rating, and it does it rather well. And in fact, it seems I overbuilt it because it's capable of doing much more than that. I since have stopped using that AC adapter, and for the last while I've actually been running it off of power tool batteries, which, as you know, are gonna have more than enough current and runtime. I got this adapter for the battery for another project that I ended up changing direction for, so it was a spare, and I just kind of rigged up one of these cables onto it, and I just plugged that into the train box, and it works. And if you have been following the comedy, you might be aware that I built a modest solar system, slapped it on the side of my house, and it charges all my batteries now, including my power tool batteries. So I have been by proxy running my trains off solar power for the last few months. It's kind of great. So the batteries, they have more than enough current I need, but what about the train box? So again, designed for about 1 amp, I get 1.5 amps of current out of this thing. I can load it down as hard as I want, and I have a hard limit at 1.5 amps. And as I believe what is going on, it's because of the inductor. As you know, this is a PWM switch mode type power supply. It has the whole MOSFET switching and the inductor on it. And the inductor I got is 1000 microhenries rated for 1.5 amps. Again, I was shooting for 1 amp. I got an inductor bigger than what I needed. 1000 microhenries was so that I could have a significant voltage drop with clean DC. I could drop 20 to 18 volts down to like 5 and down to a current of 150 milliamps, which is what this guy uses. So I can run this thing very smoothly at a crawl. The more voltage drop you need and the less current you're running, the bigger the inductor. So as where a lot of switch mode power supplies that we have in our everyday lives might only have like a 40 to 100 microhenry, I went with 1000. And I do believe that this inductor is one of the weak links that's limiting our current output. As I understand it, and I could be completely wrong, once you hit that saturation point of the inductor, it starts to actually create some electrical back pressure, if you will, that resists current. And it will only let 1.5 amps pass through it. Anything more you try to cram just translates to voltage drop. So it's kind of great because it's like built on fusing and current limiting. When my track accidentally shorts out, as you know that does happen, it doesn't overload or burn anything out because it can only let certain amount of current through, and that's not enough current to burn anything out. It also means I can go ahead and throw as many locomotives on that track as I want without actually overloading it because it won't let itself overload. But nevertheless, I want more current. So one of the things we're doing today is we're going to replace that inductor with this guy, this nice toroidal, chunky looking pupper. This identically is 1000 microhenries, but it's rated for 3.5 amps. We're gonna double our capacity. And that also means a higher propensity to burn stuff out. So that's gonna be interesting. But yeah, that should do it. However, there's more than one weak links in here. If we look at the schematic, all this stuff is pretty straightforward. This is the switching circuit. All this circuit down here is it's just a fancy solid state toggle switch. Voltage regulation to run all that circuitry. Over here is the clock generator for our toggle circuit. Indicator lights telling us what direction we're going. And then right there is our PWM generator for our power supply. We got a speed knob, some diodes, hack with this Schmidt trigger inverter that generates the square wave that we need. Over here is our power section. This is what actually takes the main voltage coming in and turns it into the voltage we want. PWM signal comes in here. MOSFET driver driving a MOSFET. MOSFET switches on and off. As you know, the MOSFET switches on. Voltage starts to rise. When we hit our target voltage, it switches off. However, while that's happening, current flows through the inductor here, charges up the inductor so that when the MOSFET switches off, the inductor takes over, its magnetic field breaks down, and it keeps the current flowing. Which brings us to this guy right here, the diode. You see, when the MOSFET's on, positivity flows through here, and out. When the MOSFET turns off, well, that guy ends up generating the current. Positivity continues to flow this way, but this side of it here goes negative. Diodes are one-way valves. When this side of the inductor goes negative, this valve opens, allowing a path to ground so that the inductor can do its job running the circuit. That's a 2 amp diode, and obviously we need that to match what we're trying to do. 3.5 amps, well, I got these guys. I only need one of them. That's a 20 amp Schottky diode. Part number MBRF2045. Now, why a 20 amp diode? Well, again, derating, and for 2 common values. Diodes come in common, all components come in common values. Yeah, they'll have values in between, but they're going to be more expensive. 20 amp is common. Also, for testing purposes, I wanted to know that this component will work for me because I'll buy more of them for other circuits, and then I'll just have one diode that can handle all sorts of different current capacities. But one claim to fame it has an insulated mounting point. You see these little chips like this, and that's usually metal. That metal is going to be connected to one of the pins, which means that metal is hot, which means you can't just strap this pupper to anything. This being plastic, insulated, it means we can strap it to anything, and we're gonna want to, because diodes have the funny effect, they generate heat. Even if you don't go anywhere near their rated capacity, I promise you, I start pumping 3 amps through this, even though it's rated for 20 amps, it's gonna put out heat. Diodes incur voltage drop automatically at least 0.7 volts. And with voltage drop means there's resistance, means there's heat generation. So you gotta keep them cool. That is one reason why you'll want a bigger diode than you're actually spec'd out for. If you just raw dog run it with no heat sinking, there's usually a D rate. That would be in the data sheet. They'll tell you, oh, it's 20 amps, but if you're just gonna run it ambient, it might only be 10 amps, for example. Now, we are gonna heat sink this, but because it's insulated, I'm just gonna find a way to strap it to the enclosure. The enclosure is made out of aluminum, and it should be more than enough heat sinking that we need. Obvious other bottlenecks are gonna be the wiring itself. The one that goes from the power supply to the output module is 20 gauge, which should be fine. This I'm thinking of upgrading right here. That's from the power in to the power supply. It's only 22, but for that shorter run, it should also be fine. You know, there's different ways to rate ampacities of wires. And like, for example, your house, you'll have 14 gauge wire to do the 15 amp service. 14 gauge wire can handle way more than 50 amps, depending on its length. We rate it at 15 amps because it's implied that in a house, there could be at least a 100-foot run as it snakes through all the walls. But if you only have a short little piece going from here to here, then it might have no problem handling significantly higher currents. So I'm not too worried about this bottleneck. What I am worried about is over here on the battery, the adapter that I made, this dinky little cable that I just kind of scrapped off who knows what, I don't even know. You just kind of cut these off old wall warts. This is probably going to have some pretty small gauge wire, and it's going to incur some sort of voltage drop going from point A to point B, and you want length, right? This is where it comes in. We have length now. That length is going to have some sort of resistance per inch. It's going to be small, but it's going to be enough to maybe take the edge off, the edge that we need. So I went online in my last order. I ordered this. Chunky boy. It's an 18 gauge. That should have no problem conducting 3 amps of current and or more. Who knows? Maybe I'll make this thing bigger in the future. But we got a bit of length. We got some more beef. The last and final and the biggest bottleneck, these guys right here, the IXDD609 MOSFET driver that we used to form, or I should say hack together, a solid state H bridge. If you don't know what an H bridge is, look it up, but it's basically 4 MOSFETs that we use to switch the phase on a motor controller if we want solid state switching. Each one of these MOSFET drivers has 2 MOSFETs in it, so we can make and hack together a quick and dirty H bridge, one on each phase. So basically, when the switching puts like a positive signal to here, this thing will output full track power positive to this side, whereas that would be negative, and then they can rotate. Whatever signal is put into here, the MOSFET driver takes full track power and sends it to the track. But it has actually quite a significant flaw that didn't occur to me. Now, in theory, it's good. They're rated for 1 amp continuous, which I believe is passively, package power dissipation dependent, as they say, 9 amps max. And I'm confident that I can get this thing to handle 3.5 amps continuous. It takes 1.5 amp continuous, no problem. And I actually started building and designing a nice little automatic fan controller circuit. I was gonna put a fan in here to keep these puppers cool. And as long as you keep them cool, like computer processors, we can overvolt them, overclock them, and get more capacity out of them. However, if we look at the data sheet and we look at output resistance, that's our on resistance. We can have a maximum of 1 ohm. Oof. If you know Ohm's law, if you put 1 amp of current through a 1 ohm resistor, it's going to drop 1 volt. And because we have 2 of these virtually in series going through, that's twice the resistance. And sure enough, even though I spec'd this guy out for like 14 plus volts, when I load her down, oh, I was lucky to get 12 out of it. I tweaked on it, raising the governor voltage so I could get up to 13.5, but still, there is a lot of voltage drop that I determined came from these drivers, which honestly, they were a brilliant idea for this, and they were an okay idea. They work okay at 1.5 amps, but they're not gonna do a 3.5. Imagine 2 ohms of resistance at 3.5 amps. I would see like 6 volts drop. That's just not gonna do, obviously. So I need to go with a more mechanical solution. So I got myself this nice little 8 amp DP-DT relay, and we're gonna be reworking that into here and replacing those drivers altogether. It's also gonna be nice to have that little click to confirm when my phase changes, because sometimes when I just kind of press the button and I don't realize that it didn't register and I'm not paying attention and the train just keeps going in the same direction, crashes, yeah. So, real quick before we do this, how about a before? All right, just to set as a baseline, we're gonna run the train as it is now before we modify the pedal. See it here, a Mod 60 car consist featuring 3 goats of the CP liver. Let's bring it up to temperature and see what kind of numbers we're getting. Notice it's a little jumpy. Yeah. It's a byproduct of those drivers and their voltage drop, not letting the juices flow that smoothly at first. All right, that's pretty much full chooch as it would. I'm getting 1.4 amps here on the ampere meter, peaking out at almost, oh, hold on, train's coming by. So as the train gets farther away, we dip down to about 1.25 amps as seen on the meter here. And then as it gets closer, maybe 1.45, we almost hit 1.5, not quite. There's resistance in the track itself when it's far away, so it can't consume as much current. The drivers are getting toasty, that's for sure. And for voltages, we're averaging about 13.5. We're seeing 13.6 there, 13.7. The voltage again goes up as it goes farther away because it can't consume as much current. As it gets closer, we see it, oh, see, 13.5. Now, let's time on it real quick. We'll set a little pointer here. Wait for it, and go. To be fair, it's got a very reasonable clip going here. Like, I think that's greater than prototypically fast. .33 seconds to make a complete lap. Now, if I knew how long my track was, I'd be able to calculate what speed that translates to. Unfortunately, I haven't remeasured it since I changed on it. Let's sort that out by the end of the video and put that right here. So that's all fine and dandy. We're gonna stress on it just a little bit more. You see, my F7 SuperDrive here has a black motor in it, and so does my cutie patootie little GP9. Those puppers are known to pull like an amp each on their own. So what happens if we set a couple of these up? Unfortunately, it's not going to pull this whole long monstrosity here. We're going to have to assemble a similar but not quite a lengthy consist, and that'll just be my passenger trains. Okay, so we're gonna put just the F7 SuperDrive on. Even though we have the controller turned up all the way, we're only seeing 11.5 volts here, and we're pulling 1 amp. One Loco pulling 1 amp. Now if I wind her up, I'm only at about 1.2 amps, but I'm still sagging down to 13.8 volts. Now mind you, that's 1 amp, that includes all the lighting. So 2 engines has got to be better than 1, right? Obviously it's going to go faster with more horsepower. Well, no, actually, because now we're sucking back the full freaking 1.5 amps the law allows to run this train, and that's causing the voltage to sag down to 10 volts. Now that is at 8. If we boost it, oh, look at that. I saw a peak of 1.7 amps here. 1.6. Still, only 13 volts. That's how much drop we're getting. Now the funny thing here is if we strategically probe on the inside of this, we can get an idea of what voltage it's actually operating at. Before our inductor, we're seeing 14.5 volts, which is pretty much what the circuit's maxed out. That's what it's governed to. So the PWM's doing its job. However, probing further down into the circuit, I cannot show it the meter because I have to hold this here carefully, but it says 13.8 volts. That's a 0.7 volt drop just from the inductor being maxed out, which is not that much. But considering on the output, once we add in the, hold on, train's coming by. Once we factor in post drivers, sagging down to 11.7. Whoa. That's a 2.8 volt drop. Hold on, train. Actually, we can stop the train now. That's a 2.8 volt drop in total from what the system's governed to the actual output. 2.1 of those volts just from the drivers alone. So they're not as bad as we thought. We were expecting like 1 volt per amp. So at 1.5 amp draw, 1.6 amp draw, we should have gotten 1.6 volts per rail. So a total of 3.2 volt drop. So that said, we're maybe getting about a half an ohm each on resistance. That could be because I'm heat sinking them. They're not resisting as much. I would imagine as they get hotter, they'll resist more. But yeah, that is the performance of this thing so far. And as you can see, it has no problem doing it. It's just hard limits. So let us and Tomato start chopping this pupper up, and then we'll see the differences after, which based on some little sneaky tests that I did prior to filming is going to be, it's gonna be way better. All right, while you were busy watching me play with trains, I went ahead and I built the new output module. Here it is. So yeah, out with the old. Pretty much, you know, it wasn't worth reworking this board. It was actually the easiest part in this situation because we're just straight up building a new board to the same footprint and specification as before. So what's going on with this guy? What we've replaced it with is we have a relay driver circuit. So we have main voltage coming in here. That is the unfiltered, whatever, 18 volts that we're feeding this. And then we pump that through a 12 volt regulator so that it can run this relay that we have going on here. This is a 12 volt relay. It is a, what is it? TE connectivity RTE 24012. 12 volt DC actuation, 8 amps. We could have used lower, but you know, that's harder on our regulator. We can use a small regulator on this because it has a high voltage. It's not going to consume a lot of current. The lower the voltage your relay is, the more current it consumes. And then this guy's going to start putting out heat, even though it's good for 100 milliamps. And well, it's very unlikely you're going to find a relay that consumes more than that. Not in this form factor. Pretty straightforward. We no longer have a disable signal like we did before. I don't feel that we need it in my testing since I've made this thing. When you turn down the PWM, it's pretty much 0 volts to the track. We only need one of the phases to switch it on and off because that directly controls our good old buddy, the 2N7000 MOSFET, which switches the relay on and off via switching its ground. It's just that simple. 10U buffer coming into the regulator, 0.1 output. We have our output capacitance here. It was 470U in the old iteration. I've doubled it up this time because I'm doubling the power, even though the 470 was theoretically enough. But, you know, just doubling everything. Yeah, little 1U absorber to the track. That's just there because. And then, yeah, out to the track. This should be ready to drop in now. We just have to do a quick rework to the control PCB. Now, the control PCB phase is controlled directly from the output of the CD4027, which is our solid state DP-DT switch arrangement with switching lockout. You basically can't shift to reverse while the train is running. We already have a 10K resistor there. We don't really need that to drive a MOSFET anymore. And ideally, we'd want to lower that to 1K, but so far it's working. So keep that in mind if you do something like this. All we gotta do now is we gotta pull main power from this. Right now, the 3 wires that run to that control board, one's half phase, one's the other half phase, which is redundant now, and the black one is the disable signal. So we're gonna take this black one, we gotta pull it off where it is and move it to a source of power, which on this board, I have added a label, or actually it's right there. It's right there. Ooh, oh. Can we do it without taking the board out? Probably not, nor would we want to. But taking this board out, not the hardest thing in the world because I made everything modular. Just remove the bouton and well, we're gonna have to remove the knob. Loosen off the pot. Yeah, I'm quite impressed in how I figured out to put this thing together. So we're just gonna pull the black wire off the disable signal and then move it over here right beside the power input. And then we're just gonna fold her over and tack her on. Duh. Should be that easy. I've determined that the green phase wire is the one that I need to use. We have a dead pin on this. Basically, one of the third pins is not connected to anything. Actually, the first pin. So we're going to repin on this guy and just put that spare wire going nowhere, and it's just gonna float. It doesn't really matter. I don't think the logic circuit's gonna care. Just get these guys ready. All right, so our pin out now is as such. Looking at the PCB, looking at the connector this way. The bottom connection is our phase wire, which is the green. The middle connection is our power wire, which is the black. And our unused wire is the white. Double checking, I didn't accidentally, yeah, no, there's nothing connected there. This should be ready to drop in. I need to fix on this switching circuit. I just randomly tacked a 100K in there. The switching on this hasn't been 100% reliable. You press the button and sometimes it doesn't register that button click. Apparently my debounce circuit here does not work well enough. You put a high-low signal into here. Basically, it has to be active. So we have 1 meg low, and then when I press the phase button, it feeds through this 100K positive, which overcomes that 1 meg, and then that 220p kind of buffers it, debounce, I think. I was a bit rusty. The way it worked, I got it 100% reliable in prototyping, but then when I put it on the board, it wasn't reliable. And half of the reason for that is because the board is way more efficient than the breadboard, the little, you know, pokey bits. So more voltage, a stronger signal is making it there. And now those values theoretically need to change. So that's a bug I still have to work out, but it's been reliable enough that I haven't had the need. You know, you just have to make sure you give it a good press. But blah, blah, blah aside, let's slap this back in here. Let's get this into place. Our little spacer, our habitant should just hold things together. Let's just get that knob back into place. And the knob itself. All right, so switch, plug it back in. This going to the power supply module. All right, so now we're ready to mount this. And I've piloted the footprint. We just slap that in there like that. And then these 2 little pieces of wire that I left hanging here, we just solder those onto the terminals. We should probably put the nuts on first, or at least one of them to hold it into nice and still into place. All right, We just need to wrap output wires around the terminals because there was no real way to integrate them. Oh, you know what? I forgot to show you the underside of this and explain the layout. It's right here. So similar layout to the other one. We got space for our cap nuts. We have holes here that represent where those wires are. There's our output, and here's our big relay. Chonking up the room. So power comes in here, bottom's positive, goes to one capacitor. We have an overland connection because we had a crossing point. Remember, if you perf board, drill out and remove the pad that's there because they're double-sided pads. If you accidentally tack to there, you can short circuit through the board. And then it goes to the other capacitor. That capacitor's, that positive bus, connects to one of the wipers in the relay. And consequently, yeah, negative comes in, connects to the other wiper. Kick on the relay, those wipers swing around. And then we just have a DPT arrangement. This is default positive out, connects to there, passes through, connects to there. And then this little C right here connects the other wipers to the output. For the switching, here's our connector. There's our phase input connected right to the 2N7000. There's our power input, goes to the buffer capacitor, input of the regulator, output of the regulator, straight to the relay. We have a ground bus coming up here because this is the negative. Obviously, we have to ground a regulator output capacitor, and then into the MOSFET out to the relay. And of course, because of how relays are, that's a 1N4007 diode. That's our freewheel diode. Because much like an inductor, this coil in the relay builds an electromagnetic field. And then when you turn off the relay, that field breaks down and tries to send a power surge back into the circuit, which could pop something like the transistor and MOSFET that's running it. So what this guy does is that little pressure relief valve opens out, lets it ground itself out. Now, the only thing to note is that I double traced all the power connections. These main lines here that connect power to the relay, and then these lines coming off the relay, I used 2 pieces of my conductor wire, not just one. So it's gonna have all those load bearing capability. All right, relay module is connected. We just need to find the cap nut kicking around in the messicles here. Secure that into place. Oh, look, there's room for the screwdriver now. There wasn't on the other board because of the heatsink. Yeah! Now our power in, our power feed from the power supply. We just, oh boy, did I make this wire long enough? I hope so. Yeah, just snip that on there. And then our control signal, snip that on there. The moment of truth. I already kind of bench tested this before I rolled camera again. The knob was up, so there's latent power. I'm gonna have to rearrange that knob. Takes a second to burn off that power, unfortunately, without a load. Oh, there it goes. Now, I hear the relay. Do you hear it? We need a dummy load. Ah, yes, the little 12-volt light bulb. We'll just kind of secure that onto there. So, how's the functionality? We have output. We press it. Reverse lockout. Oh, there it goes. See what I mean? You have to give it a slow press. And then to confirm on the multimeter, this is my default positive. This is my default negative. We should have, oh yes, positive power. We're gonna get the correct phasing direction. Press the button, and when it switches, negative voltage. It is working. It is working. Let us, real quick, update on this power line that goes to the battery. Preferably with the battery disconnected, right? Do I have more Fjorks? Hopefully I have more Fjorks. Where do I keep my Fjorks? I can't find more forks. Those might have been my last 2 forks. Oh, I forgot to order more. Okay, well, I'll have to search out some, get some more. In the meantime, we could just, they have these nice tinned ends. We might just be able to stick that on there. Yeah, pretty much. That's not going anywhere anytime soon. Nice thick boy wire. Okay, that's gonna be good enough. Oh, I got it backwards. I can't remember, does this circuit have reverse polarity protection? It might not. Plug power to this thing backwards once and poof! All right, proper 18 gauge power line. Poof! All right, it's ready to go. Aside from the power supply upgrade, we're not yet at 3.5 amps, but this hasn't been an insignificant project. So you're gonna have to stay tuned for part 2, sir, where I am going to install the inductor and the diodes onto the power supply board to bump this pupper up to 3.5 amps. But in the meantime, this should be ready to test, and that's what I'm going to do before I commit to working on it more, because you never know. Something could come up, something that I've done wrong, or maybe it doesn't like running with a relay, because I do believe those drivers that I had, their resistance helped prevent short circuits. So the short circuits weren't profound. Who knows? Now when I get a short circuit, I might outright fry this thing. So it's better that I find that out at 1.5 amps before I upgrade it to twice the power, right? So yeah, I hope you enjoyed this. If you did, stay tuned. We are going to upgrade this further, and then you're gonna see what difference it makes on my modest 60 train consist, 60 car consist, pulled by a trio of goats. It is also dinner time.